Hello everyone, I'm Herman. Our group is Classiq Entanglers, and this is our presentation for our implementation of the algorithm by Babush et al. The motivation throughout this challenge was to demonstrate a quantum speedup of this algorithm. We wanted to show quantum supremacy, hence our ultimate aim was to do practical demonstration on a 70 plus qubit system with appropriate depth. So we selected a problem formulation as seen here. The reason for this is that this is an extension of the one that authors showed to be BQP complete. The problem formulation is quite scalable, and we'll later take necessary steps so that we have a deterministic implementation without needing Oracle S. Um, there are certain things which were ambiguous to us, which we have filled in and maybe even provided some possible improvements. For example, in equation A6, the unitary is unspecified, and hence we propose using the algorithm by Shukla et al. We also use this algorithm for our state preparation, and then we just apply the Z gate. Now, the main problem of depth arises from the simulation of our Hamiltonian. Uh, for that, we need to first derive the Hamiltonian matrix itself, which requires to understand a lot of nuances of the paper, which we meticulously go through it. And then we derive the K matrix, the uh, the B and B dagger matrix, uh, do the padding procedure as mentioned in the paper, and we formulate an entire class for it to obtain it later. Now moving to the simulation of the Hamiltonian matrix, um, the depth and the accuracy would depend on the matrix itself and the selection of the methods. So we do the testing of smaller systems based on these three methods: Trotter-Suzuki, randomized evolution, specifically Q-drift, and exponential function. All of them are in Classiq and we use them. Lastly, we compare the fidelities and note down the depth of the circuits. Now my friend Ram will take over.
I'll be explaining our approach in solving the problem using the Classiq framework. We used an iterative approach to perform the Hamiltonian. So the first step is to understand the dynamics of a coupled spring mass system. We used the Lagrangian mechanics to find out the equations of motion and then solve them to identify the position and velocities. Next, we manually computed the Hamiltonian of the system using the equations mentioned in the paper. And then we tried to solve them using using the ordinary differential equations. So after once that is done, we shifted our focus to the Classiq framework. So using the masses and initial spring constants and the corresponding initial position and the velocities, we computed the initial state of the system and transformed into the quantum space using the state preparation methodology from the Classiq engine. The next step is we compute the Hamiltonian. So the novelty in our approach is that we use a deterministic way to compute the Hamiltonian instead of the oracle way followed in the paper. So in the deterministic way, we formulate using the various equations. And once that is done, we convert the Hamiltonian matrix into a sparse polyop notation, and that is the equivalent representation of the Hamiltonian in quantum circuits. So once we have the initial state and the Hamiltonian in quantum domain, we perform the next important step is to perform the time evolution of the Hamiltonian. So we use Suzuki trotterization as a major approach, and additionally we also tried quantum walks and exponential approaches for performing the time evolution. So finally, once the state vector is obtained, we parse the state vector to get the position and the velocities for various masses. So an example system which we use consists of like four masses, and these lines are the springs. We restricted the motion to 1D case. So we can see that the amplitude of the position of the mass one increases as we progress, and it's becoming a sinusoidal form. So since this is the initial starting stage, the amplitude is lower, and after that it picks up and goes on. And these are the, say other, I mean the positions are relative. So the mass M2, M3, and M4 are being a zero, since it doesn't move. The first mass oscillates and it follows that. So these positions are relative, and these are the corresponding velocity curves. Finally, we try to simulate a similar system using classical methodology in this corresponding framework, and we can see that we obtain the same values, like the magnitudes remaining the same and phase oscillates between positive and negative. So these are our references. Yeah, thank you for your time.